and welcome to Down the Spirituality and Science Rabbit Hole, podcast number 21, Quantum Field Theory, A Path to the Spiritual Realm. There are two theories in physics that give the exact same calculated results for experimental data. However, the ontology behind the two theories is very different. The term ontology refers to something's nature of being, its isness, I guess you could call it, what it fundamentally is. The foundation of quantum mechanics is generally considered to have been laid in the year 1900 when Max Planck proposed the concept of energy quantization, suggesting that energy exists in discrete units called quanta. The inception of quantum field theory is usually dated to 1927 with Dirac's famous paper titled The Quantum Theory of the Emission and Absorption of Radiation. Here, Dirac coined the name quantum electrodynamic, which is a part of quantum field theory that was developed first. Quantum mechanics and quantum field theory are two very different theories. Quantum mechanics is a theory that describes particles, hence the word mechanics. Particles are easy to visualize, but the particle picture leads to a mass of contradictions. In quantum mechanics, as is usually presented, the Schrödinger equation describes the probability of finding a particle at a given point in space. Quantum field theory, on the other hand, is a theory that describes fields. Fields are harder to visualize, but a world made up of fields is consistent and makes sense. In quantum field theory, the Schrödinger equations describe the single point energy intensity of fields that exist everywhere in space. Quantum mechanics is full of paradoxes and logical contradictions that are inconsistent with our empirical ideas of reality as we experience it through the five senses. These contradictions were so serious that the Copenhagen interpretation was developed by Niels Bohr. The Copenhagen interpretation is a collection of views about the meaning of quantum mechanics stemming from the work of Niels Bohr, Werner Heisenberg, Max Born, and several others. The use as an interpretation was apparently coined by Heisenberg during the 1950s to refer to ideas developed in the 1925 to 1927 time period, glossing over his disagreements with Niels Bohr. Consequently, there is no definitive historical statement of what the interpretation entails. An informal summary of the interpretation is, and I quote, "Just crank out the math and don't try to understand what the equations mean about reality." Now that may be a good thing for physicists, but it is not a good thing for philosophers. There are three major paradoxes in quantum mechanics. Number one is wave-particle duality. A wave and a particle are two mutually exclusive entities. A particle is a local entity, whereas a field or wave is non-local and spread out through space. An entity cannot be both at the same time. Number two is the uncertainty principle, which basically says I can't know the position and the momentum both at the same time. And number three is the role of the observer, oftentimes called superposition, which means everything exists as a probability until somebody looks at it and makes a measurement where it then becomes actuality. Modern quantum field theory has no paradoxes with our empirical ideas of reality as we experience it through the five senses. Quantum field theory may be the most successful scientific theory of all time, predicting experimental results with stunning accuracy, and it also advances the study of higher dimensional mathematics. there is actually no need for the Copenhagen interpretation with quantum field theory. Okay, we'll take number 1, wave-particle duality. Erwin Schrödinger anticipated quantum field theory. Unfortunately, Schrödinger was outvoted by all his peers. Schrödinger's famous wave equation came to be taken not as an equation for field intensity, as Schrödinger would have liked, but as an equation that gives the probability of finding a particle at a particular location. The wave-particle duality paradox can be resolved in a very simple way. In quantum field theory, there are no particles. There are only fields. In quantum field theory, Schrödinger equations does not describe a probability. It describes the intensity of a field, and fields can oscillate. The particle-like behavior of fields is explained by the fact that each quantum in the field maintains its own identity and acts as a unit, no matter how spread out it might be. The uncertainty principle. The probabilistic interpretation of Schrödinger's equation eventually led to the uncertainty principle of quantum mechanics. Heisenberg derived an equation that relates the uncertainty in position of a particle to the uncertainty of the particle's momentum. As stated before, in quantum field theory, there are no particles, and hence no position, either certain or uncertain. Instead, there are blobs of field energy that are spread out over space. Spreading out is something that only a field can do. A particle can't do that. However, there is an important difference between the Schrödinger field collapse in quantum field theory and the corresponding wave function collapse in quantum mechanics. In quantum field theory, it is a real physical change in the field. In quantum mechanics, it is only a change in our knowledge of where the particle actually is. So this takes us to the third paradox, which is the role of the observer, or what's called also superposition. In quantum mechanics, nothing happens until someone looks. So until the observation is made or the measurement is made, we can only talk about probabilities. Can it be that nothing really happens, that there are only probabilities until someone looks? Like if no one looks at the moon at night, does it disappear? So this was addressed in 2 paradoxes, one by Einstein and one by Schrödinger. Both are dealing with events that are happening inside a sealed box that no one can look into until someone decides to open up the box and see what happened. The first is Einstein's bomb, and it shows the inconsistency of the Copenhagen interpretation. Einstein proposed a keg of gunpowder that could be triggered by a quantum instability of some particle. Now, for both paradoxes, the trigger is a radioactive decay, which is considered something that is totally random. So you've got a radioactive substance being monitored by a Geiger counter, and when the radioactive substance emits a particle through decay, it's detected by the Geiger counter and it triggers some event. In the case of Einstein's bomb, it's a keg of gunpowder that could be triggered by this. Now, this is thoroughly stupid in reality, because in reality there's just no intermediary between an exploded and a not exploded bomb. For Schrödinger's cat, Schrödinger extended Einstein's bomb idea to an animal that, according to the Copenhagen interpretation, would be half alive or half dead in the box until someone looks. Both now seem thoroughly stupid. However, the resolution to this in quantum field theory, it supplies a simple answer for both Schrödinger's cat and also for Einstein's bomb. In quantum field theory, there is no role of an observer. Field collapse does not depend on an observer making a measurement. The fields evolve according to the field equations and then collapse, but neither process requires that someone be there to observe it. In summary, in quantum field theory, the paradoxes of quantum mechanics have simple, almost trivial answers. There is no wave-particle duality because there are no particles, only fields. The particle-like behavior is explained by the fact that the field quantum lives and dies as a unit. This phenomenon is called field collapse. The uncertainty principle is simply not a statement. The uncertainty principle is simply a statement that fields are not localized, they are spread out. There is no role for the observer either in quantum field theory. Field collapse occurs regardless of whether someone is looking or not. So I can hear the question coming now. Gosh, Jeff, if we're talking about religion, what does quantum field theory have to do with it? And why is it so important? Well, because when we get right down to it, fields look and feel like spiritual things. A field, and also information, are not considered material. They are invisible to the five human senses, yet they are real and can be distinguished by the human mind. Not by the brain, but by the mind. For thousands of years, Eastern religions such as Hinduism, Buddhism, and even ancient Judaism have taught that the mind is part of a universal energy field that can interact through the human mind. A type of cosmic consciousness field. However, the universe we experience with our senses, all of these religions say, is an illusion. This doesn't mean that the universe of the material is not real to us, but it is just not what we think it is. There are both scientists and philosophers that speculate on the existence of fields that are associated with human consciousness and memory, which can interact with universal quantum fields. Altered states of human consciousness, such as near-death experiences, extrasensory perception, out-of-body experiences, even meditation, prayer, and other quote-unquote psychic experiences are being scientifically investigated as a function of a possible quantum mind field. That is mind, M-I-N-D field. So understanding quantum field theory is indeed a possible pathway to a better spiritual understanding of ourselves and the universe. When Einstein was asked by a rabbi if he believed in God, he answered that he believed in the God of Spinoza. Now, Baruch Spinoza was a philosopher who lived, I believe, in the 16th century. He was a pantheist and said that the universe was essentially God. Or another way of thinking about pantheism is that God permeates and is a fundamental part of the universe. He's even a fundamental part of humanity. In the Gospel of John, Jesus does say that I and the Father are one. He also indicated that other people could share that same experience by being born again from above. The philosophic concept of a world made of fields, which are properties of space, seems to me much more satisfying than a universe filled with mysterious particles that act like marbles. There are many different types of fields, and all of them can overlap and interact with each other. From the standpoint of human sensory data, fields appear to act beyond the materialism of the realm of matter. Einstein came to believe that reality must consist of fields and only fields. In quantum field theory, the various fields, both the force fields and the matter fields, appear as separate entities, each with its own equation and its own behavior. They are not combined into a single field as Einstein would have hoped, but they are related and they are members of the same family and they do interact with each other. A field is a property or a condition of space. The field concept was introduced into physics in 1845 by Michael Faraday as an explanation for electric and magnetic forces. His experiment with iron filings that align themselves in the region around a magnet is done today by almost every elementary student in science. 20 years after Faraday, James Clerk Maxwell, created a set of equations that provided a mathematical basis for Faraday's fields. So we've been talking about fields now for about 15 minutes. What is a field? A field in physics is a region in which each point has a physical quantity associated with it. That quantity could be a number, as in the case of a scalar field, such as a temperature field, or it could be a vector, as in the case of fields such as the gravitational field, which are associated with a force. A good example of a scalar field would be a temperature field. A temperature field map, as displayed here, is a visual representation that displays the distribution of temperature across a specific area of space, showing how temperature varies from point to point, often using color gradients to indicate different temperature levels, essentially. It's a map where each location is assigned a temperature value, allowing you to see hot and cold spots within the area being mapped. The figure shows the temperature field for the Earth on a certain day and a certain time. The same temperature field could be extended through the entire universe, since everywhere in the universe has a temperature. It would be a universal field that obviously changes with time. Fields have a real existence in themselves. The idea that space can have properties does not come easy. A magnetic field can be seen by its effect on iron filings, and temperature can be measured and felt, but other fields are totally invisible to the human senses. An important characteristic of fields is the way they develop or change with time. The development and description is defined mathematically by partial differential equations. These equations describe how the strength of a field at each point in space changes depending on its strength and that of other fields at that point. The changes are local in the sense that only field intensities at the point of interest can affect what happens at that point. The way that each field type propagates and at what speed it propagates are determined by the field equations. A quantum is the smallest possible amount of field that can exist. Fields in quantum field theory are made up of tiny invisible pieces called quanta, or the plural is quantum, that cannot be further reduced. There are several different types of quantum fields. Force fields and matter fields are the two major types. Quantum of force fields can even overlap each other and yet maintain their separate identities. Okay, so if I'm saying in quantum field theory everything is nothing but a field, where in the world do we get this idea of particles? Well, because they are emitted and absorbed as individual units, field quanta act like or simulate the particles that physicists were familiar with. In quantum field theory, a particle is simply an excitation of the field. In simpler terms, particles are lumps of energy embedded within a field. So to use our temperature field analogy as displayed here, the dark red areas indicate areas of higher temperature, which is an excitation in the temperature field. Notice these dark red excited blobs are concentrated into a small area, or at least a small area in regard to the total map. These areas would be analogous to particles if this were a matter field. These particles are nothing more than concentrated high-energy regions of the field. The core of quantum field theory, which summarizes our best current understanding of fundamental physical processes, is formulated in terms of quantum fields. Particles appear as secondary consequences. sometimes called an epiphenomenon of fields. They are localized disturbances in the primary entities of the quantum fields. To further complicate matters, today the tiny marble particle view holds sway, and even many physicists who use the equations of quantum field theory daily refuse to grant reality to the fields that underlie the theory. Please understand that when I refer to quantum field theory, I mean not only the equations, but also the view that the world is only made of fields, which are properties of space. For many, it is hard to accept that the world of our senses, which says everything is made of matter, is all an illusion of the underlying field. We are not saying that matter does not exist, only that it is not the primary reality of the universe. Now, quantum field theory represents as big a revolution in our thinking as relativity and quantum mechanics put together. In fact, it combines and explains them, yet it has not penetrated much into public awareness. And so the most wonderful theory ever devised, a theory that has produced more precise agreement with experiment than anything before, and that encompasses all forces and all matter, that unifies quantum mechanics and relativity, and that reintroduces common sense into physics while retaining our intuitive beliefs in space, time, and reality. This theory has largely remained a secret. An accurate way to identify the different types of fields is to use the concept of color. Color is an appropriate tool for this job because color is something that does not exist in itself. It exists only as a property of the human mind. By using colors to represent physical fields, we remind ourselves that fields are a property of space, not a separate substance in space. The colors that we perceive in nature are also imaginary. They exist only in our minds. It is in our brain, and only in our brain, that these signals are magically, and I do mean magically, translated into the perception of color. It seems that there are 7 separate fields, 5 force fields and 2 matter fields. All of the fields have an excited state or a particle associated with them. A force field does not exert a force on another body in the classical sense. Instead, it interacts with the field that constitutes that other body and alters its evolution, causing its spatial distribution to change. This change in evolution is equivalent to the older classical picture of a particle experiencing a force. The force fields all have an exchange particle that carries the force. The gravity field has the graviton, the electromagnetic field has the photon, the strong nuclear force field has the gluon, and the weak nuclear force field has the W boson, and the Higgs field has the W and Z particles. The Higgs field is unique in that it is not a force field like the other 4. The Higgs field gives mass to fundamental particles like electrons and protons. The strength of a particle's interaction with the Higgs field determines how much mass it gains. For example, photons don't interact with the Higgs field at all, and therefore they have no mass. Protons and neutrons interact strongly, having significant mass. The matter fields have no exchange particle since the excitation of the field is the particle itself. The matter fields are the lepton matter field for light particles like electrons and neutrinos, and the baryon matter field for heavier particles like protons and neutrons. For this podcast, we will not spend much time on the Higgs fields or the strong and weak nuclear forces. Now, I need to further clarify and reinforce the fact that all these things I'm calling particles here are excitation in the fields. Common sense is choosing, whenever possible, the simplest, most intuitively satisfying explanation that is consistent with our observations. It is not easy to change our intuitive picture of matter from something that exists in space to an abstract property of space. Hopefully you may find, as I do, that the field picture of nature is more philosophically satisfying than the particle one. So once more, why is all this talk of fields important? Because the world of particles and materialism have very little room to integrate the spiritual aspects of our lives. The world of interacting fields can give us insight into possibly the nature of God, human consciousness, life after death, spiritual experiences, communion with God in prayer, ESP, remote viewing, and near-death experience, to name just a few. There is considerable research that shows that consciousness is related to electromagnetic quantum brain activity. Also, this electromagnetic field activity may not be confined to just the brain. Remember, a field is a property of the entire universe. There's an awful lot to explore here. So, at this point, I have a question. Quantum field theory has a developmental history of over 400 years, starting with Isaac Newton in the 1700s. The Hindu Rig Veda is believed to have been written between 1500 and 1200 BCE, making it one of the world's oldest scriptures that is still in use today. However, the exact age of the Rig Veda is difficult to determine because it was originally composed and transmitted orally for centuries before being written down. Some scholars believe it may be even older, with linguistic and philological analysis suggesting it could be 5,000 to 6,000 years old. The Hindu Upanishads are a collection of Sanskrit texts that were written between 800 and 500 BCE, though the ideas were originally passed down orally. The Upanishads are considered to be the beginning of philosophy and mysticism in the Indian religious history. Buddhism is over 2,500 years old, originating in India in the 5th century BCE. And let's not forget the Greek philosophers such as Plato and Aristotle. These ancient religions all have a core philosophy that states that the reality available to human senses is an illusion. This illusion is generated by a deeper, fundamental energy field, which is the true nature of reality. This is in total agreement with quantum field theory. So here's my question. Science took hundreds of years, billions of dollars, millions of experiments to collect data, and thousands of people to produce quantum field theory, which is still controversial because it is so hard to believe. On the other hand, all these ancient religions had only the human mind and meditation to develop a similar assessment of reality thousands of years ago. Where did they get their information, and how did they figure it all out? I do have an answer, but it is deeply rooted in two different modes of Western and Eastern philosophy. Just like we have the two theories of quantum mechanics and quantum field theory, there are also two very different modalities of philosophy. So when the universe seeks to know itself through the medium of the human mind, some aspects of that universe must remain unknown. The physicist Arthur Eddington put it succinctly, and I quote, "Nature thus provides that knowledge of one half of the world will ensure ignorance of the other half." So just as a knife cannot cut itself, the universe cannot totally see itself as an object without totally mutilating itself. The attempt to know the universe as an object of knowledge is thus profoundly and inextricably contradictory. And the more it seems to succeed, the more it actually fails. The more the universe becomes false to itself. And yet, oddly enough, This type of dualistic knowledge, wherein the universe is severed into subject versus object, as well as truth versus falsity and good versus evil, is the very cornerstone of Western philosophy, theology, and science. For Western philosophy is, by and large, Greek philosophy, and Greek philosophy is the philosophy of dualisms. These include the dualism of truth versus falsity, whose study is named logic, that of good versus evil, called ethics, and that of appearance versus reality, named epistemology. Now, rooted firmly in these dualisms, Western thought throughout history has continued to add dualisms of its own: instinct versus intellect, wave versus particle, materialism versus idealism, matter versus energy, thesis versus antithesis, mind versus body, fate versus free will, space versus time. The list is endless. Thus did Alfred North Whitehead state that Western philosophy is an elaborate footnote to Plato. So we see that dualistic knowledge is as contradictory as trying to make your finger touch its own tip or your foot try and step on itself. One of the principal reasons that the dualistic or the divide and conquer approach has been so pernicious is that the error of dualism forms the root of the intellect and is therefore next to impossible to uproot by the intellect. In this regard, it is true that most branches of science remain today thoroughly and solidly dualistic, hotly pursuing as they are the objective facts. However, some of the purer forms of science, such as physics and mathematics, and some of the emergent sciences, such as system theory, have dealt lethal blows to several long-cherished dualisms. So that's Western philosophy. How does it differ from Eastern philosophy? The discipline of Vedanta is a Hindu philosophy that is based on the Vedas, the sacred scriptures of Hinduism, and the Bhagavad Gita. The word Vedanta comes from the Sanskrit words Veda, meaning knowledge, and Anta, meaning the goal of or essence. Here are some key points about Vedanta. Vedanta's goal is to achieve an unclouded inner world and to exist without being troubled by the complexity of the outside world. Vedanta explores the knowledge of the human self, called Atman, and also the divinity of the supreme God, called Brahman. Vedanta is one of the 6 orthodox systems of Hindu philosophy, and it is the quintessence of Eastern thought and mysticism. Vedanta has developed into many traditions, each with its own interpretation of the Upanishads, the Brahma Sutras, and the Bhagavad Gita. Vedanta is universal in its application and is relevant to all cultures, countries, and religious backgrounds. From a spiritual point of view, Vedanta says the absolute is real. The only true existence is Brahman, the absolute or ultimate reality. Individual souls are identical to Brahman and are called Atman, or individual souls. The self is the most important idea. The self, and not our physical bodies, is what we really are in our true nature. The self is the light of awareness. The self is not something experienced in the mind, but rather the light of awareness that illuminates all experience. Finally, the self is unchanging. The self does not change as the body and mind change. There is one major and crucial connection between Eastern thought and quantum theory. In Eastern philosophy, the entire universe is a unified whole where everything interconnects in a non-local fashion. Because of this property, the human mind can perceive knowledge in an intuitive fashion. Indeed, The source of all knowledge is intuitive and can be acquired through meditation techniques. This is in total agreement with the concept of entanglement in quantum field theory. Quantum entanglement is one of the most intriguing and counterintuitive phenomena in quantum physics. It describes a unique relationship between fields that exists even when they are separated by large distances. This concept challenges our classical understanding of reality and has profound implications for philosophy and theology. In quantum field theory, entanglement is understood as a property of quantum fields rather than of discrete particles. This perspective aligns with the view that particles are excitations of underlying quantum fields. When two quantum systems interact, they can form an entangled state with properties that cannot be fully described by the individual properties of its components. Indeed, the sum is greater than the parts. Despite initial skepticism, quantum entanglement has been experimentally verified numerous times since 1980. Notable experiments include Bell's inequality test experiments and quantum teleportation experiments that use entanglement to transmit quantum states over vast distances. These many experiments have consistently supported the predictions of quantum field theory and ruled out local hidden variable theories of quantum mechanics. Quantum entanglement raises profound questions about the nature of reality, causality, and the role of observation in experimental systems. It challenges our classical intuitions about locality and realism, suggesting a deeper interconnectedness in the fabric of the universe. It is also a crucial connection between Eastern philosophy, spirituality, and quantum field theory.